Welcome to the first lecture in our fifth week of the course, Analysis of a Complex Kind. Today we'll learn about integration in the complex plane. But to begin with, let's review integration in R. Given a function f that's defined on some interval ab and is real valued and continuous, we define the integral from a to b of f of t dt as the limit of these left-hand sums. So we take f at a point tj, multiply by the next point tj plus 1 minus tj, and we add all these things up. What are these tj's? Well, we take the interval from a to b, and we divide it up into these little chunks. So a is equal to t0, the next little point is t1, then t2, and so forth up to tn. And n is some large number, and we're going to let that go to infinity later on. So right now we're dividing up this interval into these n chunks. And we evaluate f at the left-hand point of each of these intervals. So for example, f of t0 is this value right here. We take that value and multiply by t1 minus t0. What is t1 minus t0? That's this length right here. So this length is f of t0, t1 minus t0 is that length. So when I multiply those two, I get the area of this little rectangle. Similarly, I take f of t1, which is that value right here. So here's f of t1, and that's this length. I multiply that by t2 minus t1 and get the area of the next rectangle. And so by taking the sum of all these products, I'm going to add up the values of all the areas of these rectangles. Well, that's an approximation for the area under the curve. So in the limit, as n goes to infinity and these rectangles become very narrow, they give a very good approximation for the area under the curve. In other words, if f happens to be above the x-axis, just like I'm doing right here, then this integral is actually simply the area under the curve. Otherwise, if f is sometimes above and sometimes below the x-axis, we're going to take those portions that are above the x-axis and subtract from them the portions that are below the x-axis. So that's the meaning of this integral. Here's the fundamental theorem of calculus. If f is a function as we discussed above, we can define a function uppercase f of x as the integral from a to x, f of t dt. So in other words, if f is above the x-axis, the integral from a to x is simply the area under the curve between a and x. Now x is the variable, so x varies. So f of x gives you this area depending on the value of x's. If x gets bigger in my picture, then f of x gets bigger. If x is smaller, f of x gets smaller, because f happens to be above the x-axis. But you can define a function uppercase f like this also if f is above and below the x-axis. It turns out this function that you define is a differentiable function, and its derivative is equal to little f of x. That's the fundamental theorem of calculus. And why is this so useful? Uppercase f actually gives you an antiderivative of f, a function that when you differentiate it is little f. In general, we say that a function uppercase f that satisfies that its derivative is little f, such a function is called an antiderivative of f. And note the following. Suppose you found two different antiderivatives, f and g. So both of them have the property that f prime is equal to little f, and also g prime is equal to little f. Suppose you found two different functions. Well, what is g minus f prime? Well, it's g prime minus f prime, but both of these derivatives are little f, so that's 0. So g minus f is a function whose derivative is 0, and that makes it a constant function. So f and g, two different antiderivatives of the same function f, can only differ by a constant. The conclusion is that we can use any antiderivative to evaluate an integral, and you've probably seen this. Suppose little f is the function you want to integrate from a to b, and you found an antiderivative uppercase g, and the integral from a to b, f of t dt, is the antiderivative evaluated at the upper bound b, minus the antiderivative evaluated at the lower bound a. The reason for this is, if you wanted to prove such a fact, you would notice that g, this antiderivative that you found, is related to the antiderivative f from the previous page by simply a constant, where f was this function f of x is the integral from a to x, little f of t dt, of which we know by the fundamental theorem of calculus that it is an antiderivative. So what is f of a in that case? F of a is the integral from a to a, so that's nothing, that's 0. And what's f of b? Well, that's the full integral that we're actually trying to find. So we know this is equal to definitely f of b minus f of a, because f of b is the integral and f of a is 0. But now f of b is the same as g of b minus this constant c, and f of a is g of a minus this constant c. And the constants cancel out, and so you get g of b minus g of a. So that's how easy that is to prove. So how would we generalize this to c? Instead of having a real valued function, we have a complex valued function, and the function does not accept a real variable, but a complex variable. So instead of integrating over an interval, we're now in c. So what will we integrate over? The answer is we'll integrate over curves. Recall that a curve is a smooth or piecewise smooth function gamma, defined on an interval into c. We could write this function as gamma of t equals x of t plus I y of t, where x is the real part and y is the imaginary part. If f is a complex valued function that is defined on gamma, then we define the integral over gamma, f of c dz, to be the limit of these sums. We take f of zj times zj plus 1 minus zj, and the zj's are the values of gamma at points tj, and we divide the integral from a to b up into these little chunks again, as we did before. So this is a direct generalization of the left-hand sum. Let's look at the picture and understand what the sum really does. Here you can see the curve gamma. Gamma is actually the image of the interval from a to b under the function gamma. Again, we divide this interval up into these little chunks, where a is equal to t0, b is equal to tn, and this is t1, t2, and so forth. Then we look at the image of these t1, t2, t3, and so forth. So for example, the curve starts at z0, which is gamma of t0 or gamma of a. It ends at zn, which is gamma of b or gamma of tn. And in between we have a zj, which is gamma of tj, and the next point zj plus 1, which is gamma of tj plus 1. So we have all these points here. In order to form the sum, we evaluate f at zj, so what is the value of f right here, and multiply that value by zj plus 1 minus zj. Then we add up all these products and take the limit as n goes to infinity. If that limit exists, we call it the integral. In fact, we call it the path integral of f over gamma. So again, it's the limit as n goes to infinity of the sum f of zj times zj plus 1 minus zj, where the zj's are gamma of tj's, and the tj's are those little points that divide the interval from a to b up into n pieces. Let me show the following. If gamma is a smooth curve and f is continuous on gamma, then this integral f of z dz over gamma can be found by taking f, evaluated at gamma of t, multiply that by the derivative gamma prime of t, and take the integral from a to b over that product. Why is that? Here's the idea of the proof. This is the sum that we use to define the integral. To get the actual integral, you would put the limit as n goes to infinity in front of it. But let's look at the sum by itself. Zj is simply gamma of tj. Zj plus 1 is gamma of tj plus 1. Zj is gamma of tj. That makes out this sum. But now we just divide by tj plus 1 minus tj and then simply multiply by tj plus 1 minus tj. So this won't affect the sum at all because we multiply and divide by the same number. But now, if you look at this term right here, as you make tj plus 1 and tj be closer and closer to each other, this approaches the derivative, gamma prime of tj. This is approximately the derivative gamma prime of tj. So the sum is over f of gamma tj times gamma prime of tj times tj plus 1 minus tj. We often call this delta tj. In the limit, this goes to the integral from a to b of f of gamma prime of t dt. Note we haven't really defined how to integrate a complex valued function. So let's quickly look at some examples. Suppose g is a function defined from a to b and maps into c. So we can write g of t as u of t plus I v of t. Then if we write something like integral from a to b g of t dt, what that really means is the integral over u plus I times the integral over v. In other words, we integrate the real part, we integrate the imaginary part, and then put them back together. And that is how the integral over g is defined. Let's look at an example. Suppose I wanted to evaluate the integral from 0 to pi e to the it dt. You then break up e to the it as cosine t plus I sine t, and integrate the cosine function, and separately integrate the sine function. An antiderivative for cosine t is sine t because the derivative of sine is cosine. So we need to take sine t and evaluate it at the upper bound and subtract from it its value at the lower bound. That's what this expresses right here. Next, we need an antiderivative for sine t. An antiderivative for sine t is minus cosine t because the derivative of minus cosine t is minus sine t, which is sine t. So we need to take minus cosine t and evaluate it at pi and subtract from it the value it has at 0. Well, sine of pi is actually 0. Sine of 0 is also 0, so I put that all into this 1, 0 right here. Cosine of pi is negative 1. Cosine of 0 is 1, but I'm subtracting that value, so minus another 1. And here's a minus I that's in front of it. Altogether, this gives you 2i. So the value of this integral is 2i. You actually don't have to break the integral up into real and imaginary part. One can actually alternatively simply find an antiderivative right in the original form. So if you can find an antiderivative of e to the it, then you can just use the fundamental theorem with that antiderivative. Well, it turns out an antiderivative of e to the it is minus I e to the it. Why is that true? Well, let's take the derivative of minus I e to the it. Minus I is a constant that goes to the side, and so I need to differentiate e to the it. The derivative of e to the it is e to the it times the derivative of the inside function it, which is I. When I multiply through, I squared is minus 1. Together with this minus, it all cancels out, so it's e to the it. So indeed, minus I e to the it is an antiderivative of e to the it. So I can take this antiderivative and evaluate it at pi and subtract its value at 0. The value at pi is minus I e to the pi. The value at 0 is minus I e to the 0. Together with the fact that we're subtracting it, we're getting this plus right here. E to the I pi is negative 1. Together with this negative sign is plus. So this whole expression evaluates to I. E to the 0 is 1, so this also evaluates to I. So that I end up with 2i. So these are two alternative methods to find the same integral. Let's look at another example. Integral from 0 to 1 t plus I dt. Again, you could break this up into the integral from 0 to 1 of the function t dt plus I times the integral from 0 to 1 of 1 dt. And then find antiderivative separately and plug in the bounds. Or you could just find an antiderivative for the whole function instead of finding each part separately. Antiderivative for t is 1/2 t squared. Antiderivative for I is it. And so 1/2 t squared plus it is an antiderivative for t plus I. We need to evaluate that at 1 and subtract from that the value at 0. When I plug in t equals 1, I get 1/2 plus I. When I plug in t equals 0, this all vanishes. In other words, the value of the integral is 1/2 plus I. Now let's look at some examples of actual path integrals. Suppose gamma of t is t plus it for t between 0 and 1. What does that look like? Well, when t is equal to 0, gamma of 0 is 0. When t is equal to 1, gamma of 1 is 1 plus I. 1 and I is right here. How about in between? Well, I'm graphing x of t and y of t together, but x of t is equal to y of t. So we could write this as x of t plus I y of t. And I see that x of t and y of t are always the same value. Y is equal to x. Well, that's this line right here. So the path gamma is really the line from the origin to 1 plus I. We can find the derivative as 1 plus I. Just take the derivative of t, which is 1. The derivative of it is I. And suppose I wanted to integrate the function f of z equals z squared over that path. So I need to find the integral of f of z dz. By our definition, the integral of f of z dz, because f is a continuous function, the path is smooth, I can take f of gamma of t times gamma prime of t and evaluate that integral from 0 to 1. What is f of gamma of t? I need to plug in gamma of t into my function f. But the function f takes its input and squares it. In other words, this is gamma of t squared. Gamma of t squared is t plus it. That's gamma of t squared. So that's where this term comes from right here. And I need to multiply by the derivative of gamma. We found that as 1 plus I. And now I have an integral of a complex value function, and I know how to evaluate that. One way to evaluate that is to simply multiply through. So this first term here becomes t squared plus 2i times t minus t squared. The minus t squared comes from the I squared right here in the second term. And I need to multiply that by 1 plus I. T squared and t squared cancel each other out, so the first term is just 2it squared times 1 plus I. If I multiply through, I have 2it squared, so this term right there, plus I times 2it squared, but I squared is negative 1, so I end up with minus 2t squared. I could break this up into the real part and the imaginary part, so I get minus 2 times the integral over t squared, that's from the second term here, plus 2i times the integral over t squared, that's the first term. And antiderivative for t squared is 1/3 t cubed, so I get minus 2/3 t cubed evaluated from 0 to 1, plus 2i, and again, the antiderivative of t squared is 1/3 t cubed, again I need to evaluate from 0 to 1. When I plug in 1 for t, I find minus 2/3. When I plug in 0, this term goes away. But the second term, when I plug in t equals 1, I get 2i over 3, and again for t equals 0, there is no term. Altogether, I can combine these into 2/3 times negative 1 plus I. We'll be using this fact later on again, so I'll remind you of that when we need it. Here's another example. Suppose I wanted to find the integral of 1 over z dz over the curve where the absolute value of z equals 1. Now this is a notation that we haven't used so far. The absolute value of z being equal to 1 has a set denotes this circle of all those z's where the absolute value of z is 1. So it's the circle of radius 1. When we write something like that, absolute value of z equals to 1, we automatically assume that the circle is oriented this way. And most of the time, the parametrization gamma of t equals e to the it is used for t runs from 0 to 2 pi. So that's what's meant when I write something like this integral over absolute value of z equals 1. We'll see later that other parametrizations yield the same results with the integral, and that's why this notation is actually a reasonable notation. So how do I find this integral? If gamma of t is e to the it, then gamma prime of t is the derivative, is e to the it times the derivative of the inside function, which is the exponent, so times I. Now, the integral over the curve gamma of 1 over z dz is therefore the integral from 0 to 2 pi of 1 over gamma of t times gamma prime of t dt. So wherever we see z, we plug in gamma of t, and dz is replaced with gamma prime of t dt. Next, let's plug in what gamma of t actually is. It's e to the it, and gamma prime of t is I e to the it. And we see that the e to the it term cancels out. All we're left with is I. Let's pull that outside of the integral, and we're left with the integral from 0 to 2 pi of dt. You could write a 1 right here if you wanted to. An antiderivative of the function 1 is t, because the derivative of t is 1. We need to evaluate that from 0 to 2 pi, so we get I times 2 pi minus I times 0, which is 2 pi I. So the integral of the function 1 over z over the circle of radius 1 is 2 pi I. Here's another example. Same curve, z equals 1. This time we're integrating over the function z. Instead of 1 over z, we take z. So again, gamma of t is e to the it, gamma prime of t is I e to the it. So the integral over this curve gamma of z dz is therefore the integral from 0 to 2 pi. We replace z with gamma and dz with gamma prime of t dt. Gamma of t is e to the it, gamma prime of t is I e to the it. And we can pull this I outside of the integral and get the integral from 0 to 2 pi, and we can combine e to the it and e to the it into e to the 2it. So now what we need is an antiderivative of e to the 2it. And the claim is an antiderivative of I times e to the 2it is 1/2 times e to the 2it. We better check that that is true. How do we check it? Well, we take the derivative of 1/2 e to the 2it and check that it really is what we think it is. So what is the derivative of 1/2 e to the 2it? 1/2 is a constant that goes to the side, and the derivative of e to the 2it is e to the 2it times the derivative of the exponent, which is 2I. In other words, these 2's cancel out nicely, and we're left with I times e to the 2it. So indeed, an antiderivative of I times e to the 2it is 1/2 e to the 2it. I mean, I take that antiderivative and evaluate it at 2 pi, subtract from it the value at 0. When I plug in 2 pi for t, I get 1/2 times e to the 2 times 2 pi I, so 4 pi I. When I plug in 0, I get e to the 0. But e to the 4 pi I is equal to 1, e to the 0 is also equal to 1, and 1 minus 1 is equal to 0. So the integral evaluates to 0. Let's look at the same path gamma and integrate 1 over z squared dz. So far we integrated 1 over z, and we got that was 2 pi I. Then we integrated z dz, and we got that was 0. Let's see what 1 over z squared gives us. Well, again, 1 over z squared means I write 1 over gamma squared of t, or gamma of t squared, times gamma prime of t dt. Gamma prime of t is that's in the numerator, and it's I e to the it, that's this part right here, and we divide by the square of gamma of t. What is gamma of t squared? That is e to the it squared, so e to the it times e to the it, and that is e to the 2it. So e to the 2it is here in the denominator, and I can therefore cancel one of the e to the it's, and I'm left with one e to the it in the denominator, or e to the minus it in the numerator. What is an antiderivative of I e to the minus it? The claim is it's minus e to the minus it. Again, let's check. How do I check? I take the derivative of minus e to the minus it. The derivative of that is minus e to the minus it times the derivative of the exponent, which is minus I. The two negative signs cancel out. I'm left with I times e to the minus it, which is exactly what I wanted to get. So minus e to the minus it is indeed an antiderivative of the function I'm integrating, and I need to evaluate the antiderivative of 2 pi, and it's 0. At 2 pi, I get minus e to the minus 2 pi I. At 0, I get e to the 0. I'm subtracting that, but with this minus sign, I get this plus sign. The first term is minus 1. E to the minus 2 pi is 1, with a negative sign gives me minus 1. E to the 0 is 1. 1 minus 1 is 0. And again, the integral evaluates to 0. More generally, one can see the following. The integral over z to the m is equal to 2 pi I when m is equal to minus 1. When m is equal to minus 1, what I'm looking at is the integral over z equals 1 of 1 over z dz, and we showed that that was 2 pi I. For all other exponents, including m equals 1, in which case I have the integral over z, m equals minus 2, in which case it's the integral 1 over z squared, all other cases, that integral is equal to 0. So for all powers of z, the integral evaluates to 0, except for the function 1 over z. And we'll see more on why that is the case later. In the next lecture, we'll look at more examples and some first facts about complex path integrals.